Hello everyone, I am Dr. Mohammad Saad, and in this slide we will be discussing about the determination of concentration of potassium in seawater by flame photometry using the standard addition method. This is the outline that we will be discussing today. In this presentation, you will be taught about the analyte, the matrix, sample, standard addition method, flame emission photometry, and the calculations related to your experiment. And then ultimately you'll find out the advantages and limitations of the method. The sample is composed of two things. One is called the analyte and the other thing is called the matrix. Analyte is anything that is being measured by you. Simple. The substance of interest is called analyte. For example, if you are going to measure how much iron is there in your blood, so iron becomes your analyte, and everything apart from iron, everything that constitutes your sample is called your matrix. Sometimes when you encounter complex matrix situations, for example, you are going to determine potassium in seawater. We know that seawater consists of numerous cations and anions and organic acids, and generally we do not find such situations in our lab. Traditionally, whatever lab samples you have been given, you are almost sure that only distilled water is there and the analyte of interest, analyte, is there. And the matrix is quite simple, that is usually distilled water. But here we are teaching you to determine the concentration of your analyte when the matrix is complex. When you have a complex matrix, you use standard addition method. As I have already told you that seawater contains a lot of ions. Apart from potassium, you can find sodium, you can find lithium, and you can find numerous ions. So how to counter that situation? You cannot make those matrices in your labs. You do not know the exact composition of that matrix. So if you don't know anything, how can you make that in your lab? So to compensate that, what you do, you take your sample and you add your standard into that sample. So the standard contains the same matrix effect that is present in your analyte. Let me make it very simple for you. If we are dealing with potassium, we are determining potassium in seawater. We know that potassium is surrounded by so many ions. They can interfere with the analysis. But if we have a standard and we add our standard in the sample, so the added standard would feel the similar effect, and hence the effect of matrix becomes similar for our analyte in the sample and our added standard. So standard addition method is simply used where you are dealing with complex matrix. So it can compensate your matrix effects and it can improve accuracy. How it can improve accuracy? Because the fluctuations or any environmental effects that would be uh, causing error in the analyte determination, they will also be affecting your standard. So accuracy is there, improved accuracy is there, there is enhanced reliability, and as I have already told you, when you are dealing with complex matrices, complex samples, you can use that. It is only a tool. We are making you understand that this method can be used to determine your analyte concentration accurately and reliability with reliability in the samples where you have complex matrix such as potassium in seawater or iron in your blood sample. Okay, so these are the challenges that are dealt with the standard addition method. If you have high concentration of the interfering ions such as sodium, chlorine, chloride, magnesium ions, standard addition method matches your standard with the standard matrix with the sample one. If there is a phenomenon of self-absorption or ionization suppression, and because you are adding your standard into the sample, the added standard would feel the similar kind of effect, thereby making you uh, feel the real effect of these ionization suppression and enhancements. And because variable ionic strength affect instrumental response, therefore extrapolation accounts for the for remediation for these matrix effects. Now we will talk about the reagents and materials that will be used in this experiment. For that, we will be making some stock solutions. For example, to make a primary stock solution of 1000 ppm, ppm means milligram per liter, milligram of potassium per liter. So if you are going to make 1000 milligram potassium per liter, and we will give you a volumetric flask of 100 ml. So 100 ml means 0.1 liters. So you can multiply that and you will be needing 100 milligram of potassium. And because we know that potassium ions are solely not delivered, they are found in any salt. And for that, for developing potassium concentration in our standard, we will use potassium chloride. So the molar mass of potassium chloride is 74.55 grams per mole, in which 39.1 gram potassium is there. So in order to get 100 milligram of potassium, how much KCl will be needed? And simply you just multiply it with the mole ratio of potassium and you will get 0.191 gram of KCl. So what you will do? You can accurately weigh 0.191 gram on analytical balance and transfer it into a 100 ml volumetric flask. Make up the volume of that volumetric flask using distilled ionized water, and then if you mix thoroughly, you will be getting 1000 milligram per liter of potassium stock solution. From that 1000 milligram per liter of potassium stock solution, you need to make a secondary stock solution or the working standard that is of 100 milligram per liter strength. So if you have a concentrated solution and you need to make it a diluted solution, you always use a dilution formula, which you know C1V1 equals C2V2. So from that formula, we know that if you draw 10 ml aliquot from the primary stock and dilute it in a 100 ml volumetric flask, you will get 100 ppm of your working standard. Beware that this 10 ml aliquot will be transferred using primary standard glassware, that is pipette or burette. Do not use measuring cylinder to make a secondary stock solution. Stock solutions such as standards or samples are always transferred using primary standard glassware. So this is the experimental setup that you will be doing. You will be having 6 volumetric flasks, each of 50 ml. The seawater sample will be given to you and you need to add 2.5 ml of seawater sample into all flasks using pipette. And then by calculating with the dilution formula, you need to develop certain concentration of your secondary standard. In flask 1 you need to make 0 ppm potassium. In flask 2 you need to make 5 ppm of potassium concentration, that is standard. In third flask you need to make 10 ppm, then 15 ppm, then 20 ppm, then 25 ppm. So in order to develop these concentrations, you need to add these volumes of secondary stock into your 50 ml flask. Then you need to make up the final volume up to the mark using distilled deionized water. When you have make up all the volumes of your volumetric flasks, the next step would be to run these samples onto a flame emission photometer. The flame emission photometer is set at a wavelength of 766.5 nanometer. We know that alkali metals can be easily excited using a common flame, that is propane air or acetylene air flame. So that is generally LPG. LPG is generally propane or mixture of propane and butane. So the fuel is propane and the oxidant is air. So when you make a fuel, when you make a flame using LPG and air, and you set an emission wavelength of 766.5 nanometer, and you optimize the nebulizer flow and burner height, you are ready to make measurements of your samples. First, what you will have to do, you need to make it zero using the distilled deionized water that you are going to use to make up your volumes. If the distilled water contains any of the potassium ions, those potassium ions would be present in all the flasks in same concentration, so they may be set zero. It is the same procedure, it's a similar kind of procedure. For example, when you weigh something on watch glass, then watch glass can be set to zero. So the same is there. In spectroscopy, you need to zero your solvent. So if your solvent contains any absorbing species, it is nullified. Then the second thing is that take the highest concentration. The highest concentration in your case is the one having 25 ppm of potassium standard. Now put the 25 ppm potassium standard in your flame and set the emission intensity under 100%. It is because it is a relative scale. So if you do not do it and you simply set zero and start measuring your samples, what might happen is that your 5 ppm solution might show 30% emission. 10% might show 60% emission, 15% might show 90% emission, and then 20 and 25 ppm of your solutions would go off scale, which means that you would not be able to measure those emission intensities. So to prevent this error from happening, what you do, you take your highest concentration and set it under 100%, let's say 90% or 80%. So this guarantees that all of your flasks, all of your solutions would always give result, and no solution would uh, give you any value that is going off scale, means beyond 100% mark. Now you record emission intensity for each flask, and now the most critical part is the data analysis. You need to construct your graph for these concentrations. On x-axis we always put concentration. The independent variable is put on x-axis and the dependent variable is put on y-axis. So on y-axis you put instrumental response, that is the percent emission intensity, and if you plot all 6 data points, you will get a graph like this. This is the sample reading, or simply you say model reading. I have plotted these values and I have acquired this kind of graph. If you observe closely, this graph is giving you an intercept. So which means that in order to construct a good graph, you need to leave some space on the left side of your graph paper. You should not be starting your graph right from the beginning, because we know that these are the standards, concentration of standards, and even when we have not added anything, potassium was there in the seawater. So this line must give you an intercept, and this height of that intercept tells you how much potassium was there in the diluted seawater sample. So if you extrapolate this line to intercept this x-axis, this x-intercept would tell you how much potassium was there in the diluted seawater sample flask, that is flask 0 ppm, the first flask. So this much potassium was there in the first flask in which we have not added anything, and because we have diluted 2.5 ml seawater into 50 ml content, therefore we need to rectify it by multiplying with the uh, volume correction, the dilution factor, the volume factor simply. So if the intercept gives you a value of 10.5 milligram per liter, and we have got 50 ml flask in which you have added only 2.5 ml of seawater. So the concentration of potassium in seawater might have been 210 milligram of potassium per liter. Okay. But if you have a limited time, or you have limited resources, such as if you have uh, if you are talking about seawater, we have enormous amount of sample. But think of yourself in a situation where you are going to analyze blood sample of a patient. So you sometimes run out of sample as well, because in standard addition method you need a larger volume of sample, because you need to prepare so many flasks using the sample. So sometimes you do not have enough sample, so either you are running out of sample or you are running out of time. You can always use a single point formula. In this single point formula, you only need to make two flasks. In one flask you do not add any standard, okay, and in the other flask you add a particular concentration of your standard, and then you apply this formula. This formula can be found in your manuals as well. If I explain this formula to you, this is the concentration of unknown and this is the emission intensity of unknown. These two values are from flask number 1, in which you have not added any external potassium, and the denominator, the concentration of unknown and standard, means it could be any other flask. If you're talking about your experiment, you can take any flask giving exactly the data point on the line. The best data point can be chosen here. For example, it could be a 10 ppm flask point. So if you take 10 ppm flask, this concentration of unknown plus 10 ppm, I have written here 10 ppm. Okay, the emission intensity of the flask containing 10 ppm of your standard was 24.1%. You can go back and check that. I have put it in the table. Now if you cross multiply it and solve it for Cu, you get a value of 10.8 milligram per liter. And just to remind you, this value is of diluted seawater. So when you multiply it with the volume ratio, because the diluted seawater was 50 ml, in which only 2.5 ml of seawater was added and the rest was distilled in as water. So if you multiply it with the volume ratio, you get a value of 216 milligram per liter. It is good, but if you have enough sample and enough time, you always go for the calibration curve method. And if you are running out of time and you are running out of sample, then you can opt for the single point formula. Okay, so let's talk about the advantages and limitations of the method. So these are the advantages. The standard addition method compensates for matrix effects, as we have already told you. There is no need for matrix matched and external standards. And if you are dealing with unknown matrices, for example, you are dealing with analysis of iron or hemoglobin in a blood sample, or you are going to analyze mercury from your hair, or if you are going to analyze potassium in seawater, you can always use it. And it has already been validated for the determination of potassium in seawater or brackish water. What are its limitations? It requires sample volume, a considerable amount of sample volume, as I have already told you, because if you are dealing with blood analysis, you need enough sample volume. So this becomes critical. If the response is not linear over a range, then it gives erroneous results, and it is more time and sample consuming, as we've already told you. So that's it for today. That's it for the lab. If you have any other questions, you can always comment it. And if you want any other information regarding my research, you can go here, you can scan it and just paste the link in your browser, and you can have a look over my research profile. Thank you so much. Good day.